So, in the previous problem, we have talked about side-angle-side similarity. Now let's go over a more formal definition. Side-angle-side tells us that if two sides in one triangle are the same ratio as two sides in another, and the angles between these sides are equal, then the triangles must be similar. Hence, if we have a situation like AB over AC, from the smaller triangle, and it's equivalent to DE over DF in the bigger triangle, and that the angle between the sides are the same, then the entire triangle must be similar. However, and you'll probably see me do this more often, we can also compare the sides of the triangle in that manner, where we have AB, the smaller side, matching with DE, the smaller side, AC, when you take one side of one triangle and compare it with the other side of the other. It just depends on your preferences. Sometimes it's a little more obvious to use that. Sometimes it's a little more obvious to use it the other way. But we'll get to see an example of how all of this works in our next problem. So, given that AC is 4, CD is 5, and AB is 6, as in the diagram, find BC if the perimeter of BCD is 20. So, what is some of the information it gives us? Well, it labels a lot of the crucial information. The only thing it doesn't label is the perimeter. So, I'm just going to write that out somewhere off to the side. Well, what's the perimeter of BCD? That would be BD plus BC plus CD, which is equal to 20. And we could even reduce that a little bit. BD plus BC. We know CD is 5 equals 20. So eventually we would just get that BD plus BC equals 15. Alright, so we can simplify something right off the bat. Now what do we do from here? Well, we just learned about something called side angle side. Perhaps we might be able to use it. So, how many triangles do we got? We have the two obvious ones, ABC and CBD, and the larger one that encompasses both, ABD. Now, are any of these similar to each other? Well, if we look at the two smaller ones, ABC and BCD, they do not seem to share any common angles. So maybe we should not look at them first. But let's take one of the triangles, for example, like triangle ABC, for instance. Now, can we show that's similar to maybe the greater one, ABD? Well, they do share that angle A. Both ABC and ABD have angle A, so that's a good start. Angle A is equivalent to angle A, or congruent, I should say. Now, side angle side tells us that, well, are the sides proportionate or not? So, are they? Now, we can do, well, looking at, let's just say, ABC. And going off of what we know, we can make a ratio of the two sides of ABC with the angle A between them. So how about we just do a ratio of 4 over 6. The smaller triangle ABC, that's our ratio. Now we need to compare that to the larger triangle's ratio, ABD. So what would that one be? Well, the smaller side of the ABD would be the 6. And the larger side would be 4 and 5, the 9. So, are these two things the same? Well, if we reduce 4 over 6, well, they're both divisible with 2, so we get 2 over 3 equals these 6 over 9, both reduced by 3, so we get 2 over 3. Hence, they are indeed proportionate with each other, which means we have two pairs of sides and an angle between them that are proportionate. So, we do have similar triangles. ABC, ABC must be similar to A. Now be careful, because ABC, AB is the larger side of ABC. We want to compare that to the larger side of the other triangle, ABD. The larger side being AD. And then we would put the B. That has to make sense because, again, 6 is the larger side of ABC and 9 is the larger side of ADB. So now that we know that this is similar due to side angle side similarity, what can we do from there? Well, we are trying to find BC. Can we come up with any sort of proportion involving that? Well, let's list all the proportions. So AB, like we said, would match up with AD, the two bigger sides. And AC would match up with AB. Then finally, we would get that BC. This is, and again, the top parts are coming from the smaller triangle, ABC. BC would match up with DB, the remaining side. Now, we want to find out what BC is. So let's try plugging in some values. AB is 6. And AD is 9. Well, we already know that. AC is 4. AB is 6. And BC, the thing we are trying to find, is our variable. That's over, well, I don't know what BD or DB is either. So let's just write it like that. But what I can do now is say that, okay, BC over BD or DB, whatever, is equal to that fraction, which reduces to 2 over 3. And if I'm trying to find BC, I really am trying to solve for, I want, well, we have this nice little formula up here, right? BD plus BC is 15. So, how can I use that? Well, maybe if I substituted BD with something in terms of BC, I could then simplify. So taking all this, I'm going to use that trick I used in the last problem, which is that you can just flip the fractions and get BD over BC equals 3 over 2. And that would simplify, multiplying by BC on both sides. BD is equal to 3/2 of BC. And now I can simplify this formula, getting rid of BD, replacing it with 3/2 BC plus BC equals 15. Okay. Well, what's 3 halves plus, well, 1 BC? There, we don't write the 1 there, but what's 1 plus 3 halves? Well, 1 is the same thing as 2 over 2. 2 over 2 plus 3 over 2 would be 5 halves. BC equals 15. If you multiply by 2, I'm trying to think of a good space I can write this. You know what? We're just going to be real sloppy and write it all the way over here. And let me get rid of this stupid arrow. So, if I multiply by 2, I get 30 equals 5 BC. Divide by 5 to get that BC is equivalent to 6. And that is your answer. So now we have a great example of how to utilize side-angle-side similarity.